All right. Hello, everyone. Today, we continue from where we stopped at 2023 NECO Physics past question solution, question 12d. So question 12d says a piece of copper of mass 400 grams at a temperature of 580 degrees Celsius is quickly transferred to a vessel of negligible thermal capacity containing 200 grams of water at 30 degrees Celsius. So from here, let us bring down what you have. Solution. So given that the mass of copper, so we are going to represent it with M subscript C. It is given to be 400 grams. So we have to change it to kilogram by dividing by 1,000. That will give us 0.4 kilogram. And at a temperature, that is the initial temperature of copper, is the temperature of copper is 580 degrees Celsius. You can see it's very high, right? Above 100 degrees Celsius. So it's 580 degrees Celsius. So we have temperature of copper, we use theta subscript C to represent temperature of copper, and it is 480 degrees Celsius. So you can assume how it's going to be. It's going to boil the water, overboil the water. That is it. Just assume how it's going to be. If we dip it inside water, the water will boil, right? So, and transfer it into water, a vessel containing 200 grams of water. So mass of water is M subscript W to be 200 grams. Convert it to kilogram divided by 1,000. That will give us 0.2 kilogram. So, and the temperature of water before the copper was transferred into it is 30 degrees. So, temperature of water, so I'll use theta W, and it is 30 degrees Celsius. So if the final steady temperature of the mixture is 100 degrees, so at the point of at the time the copper was transferred into the water, then the steady temperature of the mixture is 100 degrees. So say temperature of mixture is 100 degrees Celsius. So let's just use ordinary theta to represent temperature of the mixture, which is 100 degrees Celsius. Are we together? You can imagine during Harmattan period, you boil water at over 100 degrees Celsius and you pour it into a water that is a bit cold or at room temperature. So, the water you poured into it, the hot water, initially you cannot dip your hand into it, isn't it? But by the time you poured it into the cold water, you'll be able to mix it with your hand. So that temperature at which you're able to mix it, that is the steady temperature. So that is it. So the steady temperature will be lower than the temperature of your water. Maybe the temperature of water, boiled water, is 100 degrees Celsius, and the temperature of the cold water is, let's say, at room temperature, 25 degrees Celsius. So by the time you pour it into it, you now have a steady temperature of the mixture to be, let's say, 60 degrees or 70 degrees Celsius. I hope you are getting it now. So that is what happened here. By the time the copper at 580 degrees Celsius was dipped or was transferred into the water was initially at 30 degrees Celsius. So the temperature of the mixture now become 100 degrees Celsius. So the question is now asking you to calculate the mass of water that boiled away. Remember, I told you that the temperature of that copper is very high, 580 degrees Celsius. Therefore, if you put it inside the water, it's going to boil, right? It's going to boil, and the liquid is going to turn into a vapor, right? So that will boil away. So we are given all the other parameters, such as the specific heat capacity of copper, that of water, and the latent heat of vaporization at the point where the liquid is being transferred, is being are changing a phase to vapor. So at a temperature, at a steady temperature, right, the heat is high, but the temperature is not seen. That is, it's not visible. So latent heat, we call that one latent heat, when there is a phase change at a constant temperature. I hope we are getting it. Okay. So now the scenario behind this is that there's going to be a kind of heat transfer from one source to another. So now you can guess which of these will transfer heat and which of these will gain heat. So there are two things here, or three things rather. The copper at a high temperature is one that will lost heat to the water at 30 degrees Celsius. And as well, at the point where the liquid is going into vapor, the liquid absorbs heat, right, from copper as well. So that's what we're going to do now. Now, we are going to have at a steady temperature, heat gain is going to be equal to heat loss, isn't it? So heat gain or heat lost by copper is the same formula. Let's use H copper is equal to MC change in theta. So now that will be equal to mass of copper, MC subscript C, and specific capacity of copper will be C subscript C, then change in temperature. So it's going to be mass of copper, specific capacity of copper, and change in temperature here is going to be temperature of copper minus temperature of the mixture. Are we getting it now? So if you do that, then heat lost by copper, Hc, will be equal to mass of copper is 0.4 multiplied by specific capacity of copper is 4.0 times 10 raised to power 2 multiplied by the change in theta, change in temperature. Temperature of the copper is 580 minus the temperature of the steady temperature, which is 100 degrees Celsius. So from here, we can just multiply all this together. That will give us 160. So I have 160. Then multiply by the change in temperature, 580 minus 100. That will give us 480. So I have 480. So this will be equal to 480 multiplied by 160. We end up having 76,800 joules. So this is the heat lost, the amount of heat lost by copper by the time it was transferred into the water. Good. Now, so let's look at heat gained by water, heat absorbed by water at 30 degrees, that raise it to 100 degrees Celsius. Okay, so let's heat gained by water at 30 degrees Celsius, raising it to 100 degrees Celsius. So let's take HW as the heat gain, which is equal to M mass of the water multiplied by specific heat capacity of water, then multiplied by change in theta. So this will be mass of water, specific capacity of water, into bracket. The change in temperature here is going to be temperature of the mixture minus the temperature of water. Good. Now that will be equal to mass of water is 0.2. Specific capacity of water is 4.2 exponential 3. So have 4.2 times 10 raised to power 3. Then change in temperature. The temperature of the mixture is 100 minus temperature of water is 30 degrees. So let's press our calculator together. Here now, that gives us 840. 840 multiplied by 100 minus 30, that will give us what? 70. So if we do this together, multiply by 70, that will give us 48,800 joules. This is the amount of heat absorbed by water at 30 degrees Celsius that raise it to what? 100 degrees Celsius. Are we together? So now we are going to calculate the heat absorbed. The heat absorbed by liquid water at 100 degrees Celsius, changing to steam water, right? There's a phase change here at a constant temperature, changing to steam at the same 100 degrees Celsius. There's no change in temperature. So that heat absorbed by liquid water, we call it mass times this specific latent heat of vaporization. So that will be equal to, mass is what we're looking for. That will be mass of the water that boiled away, multiplied by the specific latent heat of fission. It is given to be specific latent heat of vaporization, rather, of the steam is given to be 2.26 times 10 raised to the power 6. So 2.26 times 10 raised to the power 6. So that is it. Now can come together now here and say heat loss by copper will be equal to, at equilibrium, will be equal to heat gained by water at 30 degrees Celsius, right? Raising it to 100 degrees Celsius, plus heat gained or absorbed by liquid water at 100 degrees Celsius, changing to steam at the same 100 degrees Celsius. So now let us put the value. Remember, we have calculated heat loss by copper. That was 76,800. So I have 76,800 is equal to heat gained by water at 30 degrees Celsius is 58,800 plus the heat gained by liquid water, that is 2.26 times 10 raised to the power 6 M. So by the time this one cross the equality sign, I'm going to have 76800 minus 58800 equal to 2.26 times 10 raised to the power 6 M. Are we together? So take your calculator again, press 76800 minus 58800. That will give us, let us put the one we are looking for to this side. That will be 2.26 times 10 raised to the power 6 is equal to 18,000. So here now, divide both sides. Here is M here. Divide both sides by 2.26 times 10 raised to the power 6. 2.26 times 10 raised to the power 6. This one cancel this one. We have M equal to, so raise your calculator. What is 18,000 divided by 2.26 exponential 6? That will give us 7.96 times 10 raised to the power raised to power minus 3 kilogram, which you can convert to gram to give us a 7.96 gram. So the mass of water that boiled away is 7.96 gram. Out of how many? Out of 200 gram of water initially present in the container. I hope this is understood. So anytime you see a question in Latin specific capacity or energy measurement, and you are seeing either specific latent heat of vaporization or specific latent heat of fission, you should know that something like this is bound to happen. So that is all for this one. Thank you for watching. If there's anything you don't understand, please drop a comment so I can give a better explanation. Thank you. We meet in the next class.